There are two types of operations. One is basic operation. The second one is the operation to explain or to describe the change of vectors. So for the change, that is calculus. After we're talking about the basic operations of vectors, now we want to talk about the change of vectors. Oh, here we already had 3, so let's do 4. Part 3 is vector algebra for the basic operation of tensors. Now we want to move to part 4, and it's vector calculus. And this part is for the change of vectors. And to discuss the change of vectors, we want to introduce some new operators or symbols. So the first symbol is this one. We can call it del, or somebody call it a nabla symbol. And the meaning of this one is gradient. Or in other words, it's just a slope. For example, for one space, slope is just the direction along which we have the fastest change occurring, right? For example, if we're climbing a hill, when we stand at one point, we have infinite number of directions that we can go, right? But we know that we go along different directions, the height, the elevation will change at different speeds, right? And along one specific direction, the height will change in the fastest way, most quickly. That direction is the slope. So that's gradient. And in 1D case, we use derivative, right? And we talk about in 1D, we talk about derivative if it's a ordinary differential. For example, if we have a function y is a function of x, then the derivative, we usually say y prime or dy dx, right? And in 2D or 3D, so when we have more than one independent variable, let's say, in this case, let's say u is a function of u, x, y. In this case, when we are talking about derivative, we want to talk about which direction we are talking about. It's along x or along y, right? So in this case, we have ux, that is partial u, partial x. And again, this symbol, some people also call it del, and some people call it like partial d or d. Partial d, curly d, but the most comprehensive way for pronouncing this symbol, partial del u del x, is that the partial derivative of u with respect to x. That's how we say it in a comprehensive way in this one. So make sure you know how to pronounce it. That's the partial derivative of u with respect to x. But a simple way, just partial u, partial x. That's a simple way. And now gradient. So it's just one way to generalize the definition of derivative in 1D and 2D. So I just give out its formulation directly. So D is like this. So if we write it out using the full notation, it's going to be like you want to write it down using an array notation. It's going to be look like this. Some people represent it as it has 3 components. So this is the formulation of the gradient. So this is the first one. And then let's say what's going to happen. Example. So what's going to happen if we have the gradient of a scalar? You can see that this nublar sign here is just like a vector, right? So here this is just like this is a scalar vector, so this is like a scalar multiplication. That's what we introduced in the basic operation of vector analysis, right? So you just need to multiply u with each term of this vector, this component of this vector, right? So what's going to happen for this one is partial u partial x ei j. So this is the first one. Second one is a symbol called divergence. And divergence is just, so we have a nublar symbol and we have a dot product on the right of it. So that is divergence. So divergence, you can see that is just the combination of a vector and a dot product sign, right? So let's see what's going to happen if we have something like this. If we have the divergence of a vector u, what's going to happen? This is just a dot product of 2 vectors, right? So what we're going to have is times, a second, here, there's no u here, there's a dot sign here, u, j, and e, j. And for the dot product of E and EJ, we will have this. So if we write it down using the Einstein convention, it's just like this. Summation convention. So some people, write it in another way. Some people try to write it in another way. UI I. Some people write it in a simple way like this. So this is divergence. And the meaning of divergence is a source. For this divergence of u, let's take a look at one point. We assume that for one point, if we zoom in, we're going to see we have a field called u. And if we do a divergence of u, what happens is that what we get is we get the divergence of u is just the source in this region. And we know the meaning of source. That is, if we have, for example, if we are talking about heat, that means how fast heat can be generated in this at this point. So that's the meaning of it. The divergence of field is the equivalent source at this point. It's equivalent because we know that when you have u, some u will get inside of the point, some will get outside of it, right? So we want to see how this u will change the amount of content inside this point. We just use divergence, and you will tell us the source. The source tells how fast the content will accumulate inside the point. So that's the meaning of source. So this is divergence. Next one is curl. So curl is just like the combination of nabla symbol and a cross product. We can only have the curl between two vectors. So in this case, the nabla symbol operator we can view it as a vector. So that means this curl can only be used on vectors. It cannot be used on scalars. So let's take a look what's going to happen if we do a curl of a vector u. And you guys know the definition of the cross product, right? So now you can write down the curl of u. It's just a determinant of a matrix EI, EJ, EK. And now the first one, because it's partial over partial xi, and the partial over partial xj, and the partial over partial xk, right? And here we have u, I, uj, uk. So this is curl. And another thing is even more complicated, so it's called Laplacian. So Laplacian is defined as the divergence of a gradient. And here u can be a scalar or can be a vector. So let's talk about the simplest one, when u is a scalar. So this one, because we have two nabla sign here, so some people prefer to write it as nabla sign squared u. And then in an even simpler way, some people write it as this, delta u. So it's also a triangle, but now this triangle is pointing upward instead of downward. You can try to derive it yourself to find out what's the definition of it. So the definition of this, if you do it, you first get the gradient of u, and then you do the divergence, and you will find this will give us something like this. So could you guys try it yourself to see if you can get this? So try to derive it yourself based on what we learned about the basic operations and the calculus symbols that we just introduced. How to get this? How to get it here from here to here? You try it yourself first. You try to do it on one piece of scratch paper. You see, you can derive this formulation for Laplacian. So it's 2 steps. First, get this, and then do this, based on what we just introduced. So let's do it together. So how to get this one? Let me show the derivation here. So this one, we know that is just right? And then second step, we want to get a divergence of this one. So what's going to happen is that this one is just so let me write them together. Let's use different. Let's use J. And we know that we have a dot product. You know, these two E will be cancelled. Oh, sorry. This 2E will be cancelled, and eventually we will have this. And this is how we get Laplacian. Oh, back to here for the meaning of a curl. So curl also has a meaning. The meaning of a curl is a tendency of rotation. So think about it, also think about a field of U. So for U, you know that, for example, let's think about it in the water flow. What?
Shouldn't be x squared? Yeah.
Oh, this one? Sorry. Here we go.
And
about
this one? No, shouldn't be x squared or u? No, the x squared. No.
Which one?
The last one that you just changed.
This one?
No, the one that you just changed shouldn't be x.
no, the first one is.
You're right. The 2 should be here.
Yeah.
And also a 2 is missing here.
And the middle one.
The middle one?
Second one.
J.
Right, yeah.
Here? Okay. Yeah, the wrong position. Here. Should be here. And for curl, the meaning is tendency of the rotation, because if you think about in the water movement, we know that sometimes we have vertex. So something in water moves around one point. For example, if we do a curl of a vector, for example, the velocity field, then what we get is that the tendency of the rotation at every point in that field. So we know that this curl of something will give us a curl of vector will give us another vector. So that is, if we do a curl of a vector field, we will get another vector field. And that vector field at every point, we will get the tendency of rotation. So this is Laplacian. And then for this, all of the above calculus operators that we just introduced, here I want to emphasize one rule. That is the operators the above operators takes effect on the variables on its right side. So that means for example, these and these are two different things. So that's one thing that we need to keep in mind. And the last part of today's lecture, I want to introduce theorems, a few theorems that you need to learn about. Actually, you have learned these theorems before. And the first one is called Green's. In the you learned them in the calculus at the college. But mostly that's for scalars. Here we want to talk about these theorems for vectors. So the first one is the Green theorem. And for this one, we have the following things. So here, Green theorem, this is for 2D. So S, that means the surface, and the ds, that's a surface element. So integral of this divergence of U on the surface S, this one equals a line integral. So here, that's how it works. This is S. It's 2D, and this is its boundary. It's a line. Let's say it's del S. And N here is actually a vector. So N is the unit outward vector of the boundary of this surface S. So this is the unit. We're going to see this N a lot. And this is the direction of S. So again, what does the product of F and N mean? So F here could be a tensor of any orders. So it could be a scalar, could be a vector, could be second order or higher order tensors. So what does what's the meaning of a dot product? So we have a product of U and V. What's the meaning of it? Projection, right? It's just like, we have something, we project one onto the direction of the other one. So here, you can see that we have F and N here. So N is the direction of this unit outward normal vector, right? So what we do by getting a dot product of F and N is that we're trying to get the projection of F along the direction of N, right? And also the magnitude of N is 1, is a unit outward normal. So that means the magnitude of F will not be changed. by doing this operation. So what we do is that we want to get the projection. So what happened is that if f, for example, if f is, let's say, is a vector, is a move around. So what's going to happen is that if we do this, then we want to say how much f do we have along this n direction. And when we want to see how much things will get into a, for example, let's say if we something like this, n is like this, and if we multiply the f, for example, the dot product of f and n, then just would be how much materials, will get out of f will get out of n along this boundary segment. And this, again, this is the source. And this is the projection of f along n. So in this case, the meaning of this equation says that, for this S domain, the source, that's how fast, the amount of quantity will change with respect to time, equals how fast, the materials, will get out of the boundary. Can you guys understand this? So let's think about it in this way. For example, in this classroom, and let's say we have a heater here. And the way to understand it is that the heater can be understood as a source, right? If you have a heater here, the heater will generate heat. And the heat will, let's say that you generate heat, and the heat will move out of this classroom. So the heat generated by the source equals to the heat getting out of this classroom through all the walls and the floors. Can you guys understand this? So they're equal. Let's assume that if the heater generates some heat and the heater will need to get out right away, then the meaning of this equation is that the heater generates some heat, the heater generates some heat, and that heat will get out through the walls. So the total heat moving out through the walls will be equal to the total heat generated by the heater. So that's the meaning of this equation. And again, we know that the meaning of divergence is source, and the meaning of this one is the projection along n. It's just like we have this f here can be understood as heat flux. So heat flux is a vector. So it has a magnitude and a directions. So it moves out of the wall. So the projection is that, what do we calculate how much heat that moves through the wall? We know that the meaning of the integral is just summation. Just add things up. So here, this surface integral is that we just we calculate the source at every sub area of this domain. We add them up. So that's the integral, surface integral. So ds is just like it's an element ds. And a dl, again, is just like a small element of it. Right? So on the left is a surface integral. It's just like, for example, in this room, we have infinite number of heaters at every spot. So if we want to calculate how much heat was generated by all these heaters at different spots, we need to do a summation to add all the heat generated by all the heaters, right, at every point. And if we do that, if it's discrete, then we say that's addition or summation. If now it's continuous, then we do integral. Right? So the integral of ds is at every point. And then the second one is a line integral. So in this case, we calculate heat through every surface segment. And we calculate, for example, the heat moves through this segment and another segment, we add all of them up. Then we get a second integral. So in this case, it's the integral through this L, line segment. So this is the first theorem. The second theorem is called Stokes theorem. And Stokes' theorem is like this. Okay, so to differentiate, let's do it in this way. So this one is a little bit hard to understand. And here, this so in this case, we have, this is not a 2D anymore. We are talking about, for example, a patch of on the surface of a ball. So it's like a curved surface. So this is the curved surface. So this is not on 2D. This is actually 3D. And its boundary is a 3D. It's a line in a 3D space. And the segment of it is dr. And a patch of this one, let's say this should have a direction. And this one is d epsilon. You can see that it is a vector. And the direction of it is the outward normal. It's n of this patch. It's a 3D space. Just like here, let's say that this is the surface. And because we know that for every small patch of it, it can have a different unit normal. So this is also a vector. So the meaning is a little bit hard to understand, so here we don't get into it. And the third one is Gauss's.
Excuse me. Is it dV as volume?
As dr here, sorry. So it's Gauss theorem is very similar to Green's theorem. An easy way to understand it is that, now for Green theorem we are talking about, in 2D, and in 3D, actually, the Gauss theorem just corresponds to the example that I just explained. That heat generated by the heater and the energy moving through the wall. That's actually Gauss theorem, not Green's. Green is just like the version of Gauss theorem in a 2D space. So this one, we have this. So if you want to, another way to do it that, some people prefer to add another sign here. Means that this is a surface integral, 2D. If it's just one, that means it's a line integral. Here you can see that there are three integral signs here. That means the volume integral. Some people prefer to do it in this way. But it's actually does not matter. You can use one integral here, as long as you know that this is a volume, omega is a volume. So you can see that here, this is very similar to the Green theorem. It's very similar. But here, the difference is that here is not a surface integral. On the left-hand side of the equation, we have a volume integral. This is, the volume is omega, and the dV is just like a volume element. And here, on the right, so this is a 3D space, that means on the right, you're going to have a 2D. So this is the surface integral. In the Green theorem, we have a surface 2D on the left and have 1D a line integral on the right. Here, in Gauss's theorem, we have 3D integral on the left and a surface integral on the right. And for the surface integral d sub ds here, that means this is a vectored surface. So it's a surface element, but we know that every surface element has its own direction. So it's a vector. And the direction of that surface is the direction of the outward normal vector. So we can understand the Gauss' theorem in the same way as the Green's theorem. It's just like a 3D version of it. So this is what we need to know for vector analysis.
I think I'm falling for you.